we're saying is I have, like, imagine this to be a material, like this is like a glass slab or something, right? This is the width of a glass slab. So I'm denoting this direction as X and this direction as Z. So I have something like, confined to a plane here. And then we are looking at sort of a one-dimensional case for the simplicity, right? In reality, there is no one-dimensional thing, right? Because you have to have, no matter how thin you make something, it will have all other dimensions, right? So here we're sort of conceptually talking about a refractive index that varies only along X, right? In other words, what we're saying is we can sort of think about dividing this region into subregions, which so dividing this into subregions, right? And I can sort of put, this as like some N0, some N0 plus some delta N, N0 plus 2 delta N. It could be any which way, it's just varying. It doesn't have to vary linearly like this, it could be varying in some other fashion. It's just a function of X. But we're only considering in the X direction. What do we mean by that? We mean to say that, let's say a ray of light is entering here at some angle theta, right? Then what do? We first draw the normal, right? So that would be the normal. And so it is going from N0 to N0 plus delta N, so more dense. So it is going to bend towards, right? So it's going to bend something like that, right? Now, notice that this ray is going to travel here. So it has to travel along Z direction to go there, to go to the next boundary. So when we say N is varying only along X, we are not considering how N is varying along Z. In general, if you really want to consider a realistic scenario, you will also have to divide this into parts like this. Right? So as the ray is going from one black within this, it's traveling like this. But if in general, refractive index need not be constant along Z direction, that could also be changed. Then you will divide it vertically into pieces. So then you would see first, how it goes this way, you combine both, 2 dimensions, right? So for now, we are only going to consider one dimension, N of X, right? And then you can see that now again, I can draw another normal here, and it would bend some more, right? And so on and so forth. So in general, if we have a medium, this is X, and N is varying along X, and this is Z, then based on how the medium is, how the refractive index is varying, the ray path would look like that, right? It's continuously varying, right? So then it will look like a smooth curve, right? Or it could look based on how we make the refractive index, right? How we change the refractive index, we can bend it up, we can bend it down in different ways. And this is what we use to derive the equation, right? For example, if you take a small segment here, the small segment is what we call as ds. And then we have dz here, and we have dx here, and this angle is theta, right? So we saw that ds squared is equal to dx squared plus dz squared. And we also saw that cosine theta is equal to dz by dx, right? And then if you take this, and do the derivative with respect to ds, right? Then you would have basically 1 plus dx squared, so 1 is equal to dx squared by ds squared plus dz squared by dx squared. And we saw that this is nothing but sine squared theta plus cos squared theta is equal to 1. Right? So this is sine squared theta and sine squared theta. Now, instead, if you did with ds, instead with dz, take this equation and divide it by dz, then you would get ds squared by dz squared is equal to dx squared by dz squared plus 1. And we saw that then you can write dx squared by dz squared is equal to ds squared by dz squared minus 1. Now, notice that ds squared by dz squared, right? dz by ds is cosine theta. And recall that we defined theta as n of cosine theta. So then I can write cosine theta as this is a function of x because it's varying. So cosine theta as n over x. So 1 over cosine theta would be n of x divided by beta, which means from here, if I were to invert it, ds by dz is equal to 1 over cosine theta, which is equal to n of x by beta. Right? And so I can take this and plug it in here. So I would get n of x by beta whole square minus 1. This is the equation that we derived in the last lecture. This is the Ray equation. I'm going to write this equation on the next slide again. So we have dx by dz whole square is equal to n of x by beta whole square minus 1. Now we're going to make this into a different form. So what we're going to do is take this equation and apply d by dz on both sides. Right? It's an equation, right? So left hand side is equal to right hand side. So do the derivative with respect to z on both sides. So if you do d by dz of dx by dz whole square, what do you get? What is d by dx of x squared? That would be 2x, right? Right, so this would be 2 dx by dz, but then this is also a function of z. Dx by dz is also a function of z, so you have to differentiate it again, right? So you would get d by dz of dx by dz, right? Did you follow that? And so that would be the derivative for the left hand side. How about the right hand side? N of x squared by beta minus 1. Clearly, for the second term, the derivative is 0 because the second term is just a constant, it's just 1. So d by dz of 1 is 0, right? Are you following me? So all that we have left then is d by dz of n squared by beta. Beta is a constant, so I can pull that out of the derivative. So I would have 1 over beta dn squared by dz. Now notice here, we said n is a function of x, and x is a function of z. X is a function of z, meaning the ray is going to curve, right? If x is equal to z squared, then it would be like a parabola, for example, right? So then n is implicitly a function. You can write n as n of x And this x itself is a function of z, right? So when you do dn by dz, you would get dn by dx times dx by dz. N is varying with respect to x, and x is varying with respect to z. That's what you need to say when you say d by dz of n. Sorry, my n's and x's are very similar. So we can write then this as 1 over beta dn of x squared divided by dx times dx by dz. So now these two parts should be equal because we just basically did the derivative on the left-hand side and the right-hand side. So then I can write this as 2, let me use a different thing. Two dx by dz, d by dz of dx by dz is equal to 1 over beta dn square of x divided by dx or dx dz. Notice that the dx by dz's cancel out on both sides. You can move the 2 to the denominator here, move the 2 here. And this is just the double derivative, right? This is just the double derivative, d square x by dz square would be equal to 1 over 2 by 2 beta dn square x by dx. Right? This x is a function of z if you want to write it explicitly. It's the same equation as the other one. So these two equations are the same thing. They have the same information. It's just a different way of expressing it with the double derivative. Did you follow that? It's very simple, very straightforward. Okay. Now, let me ask you a question. So you see here, the medium refractive index is varying, then we say that the way of light travels like this. But doesn't light travel in straight lines? Have you never taught in childhood that light goes in straight lines? Like you take a beam of light and then you see the laser light, it goes in a straight line.
It goes straight in a consistent medium, right? Well, like it'll go straight in whatever medium it's in, but if the medium is changing, it will change.
But more than that, I want you to think about what is a straight line. How do you define a straight line? So let's say I have point 1 and point 2. Say, okay, just connect them. That's a straight line between 1 and 2. What this is doing is it is doing excessive abstraction. What we mean by excessive abstraction is we are considering as if this 1 and 2 are situated in some sort of emptiness. This point 1 and point 2 are sort of situated and there's nothing else around, right? And everything is flat. So like in this room, right? We're sort of considering, okay, that point and this point, you can just connect them by a straight line. Right? We're considering the space here to be flat. Right? What about if you want a straight line on a sphere? What's a straight line on a sphere? How would a straight line look like on a sphere?
On the equator.
No, there could be any between any 2 points, right? Straight lines between any 2 points. Let's say, you're on Earth, right? Spherical, right? So you say you go from one point to another point. Now really, if you look at it, if you go from this point on Earth to this point, see how it is curved. That is a straight line. You just think it is flat because you're so close to it, right? So you see this is flat. But, you know, if you zoom out and look, this should be the straight line. So in fact, if you draw a triangle in a flat space, what is the sum of angles? 180. How about if you do this on a sphere? Right? Now imagine you're walking, imagine a sphere, you're walking along the equator, right? And you take a turn upwards, right? So you walk like this, and you take a turn upwards. So, and then come back here again. Walk like this, go up, come back down. But now your straight lines are not like this. The straight lines are along the surface. So when you're going along the equator, right, and you want to go up to north, then you have to take a 90-degree turn. Each of these turns is 90 degrees. On the surface of a sphere, each of these turns is 90 degrees. So some of the angles in this triangle would be 270. Because here you are thinking about straight line as this, but straight line is not this. Straight line is determined by what you're on. How is the thing, the environment around you, right? So light's still going in a straight line. When you say this light ray is curving, it's not curving. It's actually going in a straight line. It's that, like how straight line looks like a curve on a sphere, like a geodesic, that's what you call it, a geodesic. What this is indicating is that the space within this thing is curved. And it just follows the space. That curvature, then you can see, is similar to the refractive index. You following me? So this is like saying that the curve is the straight line on a sphere. This is the straight line for this medium. The refractive index is such that the space inside this is not flat. And whatever that space is, this corresponds to that because it goes along the shortest path. It's going always along the shortest path. Are you able to see that? Are you able to appreciate it?
When I see the derivative, I think rather it's just infinite straight lines. You know, like the straight lines are so small that it appears as a curve. You know what I mean? Like the summation of.
No, that's
because of how we have.
There's no infinity in reality. This is not. This is really a physical thing, right? So it's not. You cannot really divide this into infinite number of parts. It is potentially divisible into an infinite number of parts, but not really, right? So your concept of point, like when you say in the derivative limit delta goes to 0, you're assuming that it is infinitely divisible and you're performing the limit as it happened, but you cannot divide a thing into infinite parts in reality. So you don't really actually have points. So no matter how fine you go, right, it's still curved. It's curved according to the thing, right? So it's not that it's a bunch of straight lines added up giving you a curve, so it's a straight line. You're again sort of over abstracting it. That is the problem with mathematical space. You're thinking about it on a plot of x and z. That plot has no physical meaning, right? But this is a glass slab. Think about it as a glass slab. You're going along a glass slab, right? So this would go along a direction like how on the surface of sphere you would go along the direction of the sphere. This light is going along however this medium is, right? So that would be a straight line. So don't try to think about it in terms of mathematics because that itself is like, you know, you have to understand calculus more deeply because there you would be over abstracting and sort of considering it again as a Euclidean space. Euclidean space means it's flat. There's nothing like how we drew flat lines here, right? But what it is saying actually is that when there is refractive index, the space in that to light is non-Euclidean. So it's still going along a straight line, but the space in the glass slab is non-Euclidean. Am I making sense? Okay. So now you can think about doing some cool things. Now you have the equation, right? You know how to derive this equation here. D squared h by dz squared is equal to 1 over 2 beta dn squared by dx. This is the equation that you have. And in fact, in general relativity, if you do whatever Einstein's equations, you basically get something like this again. But instead of refractive index, you would have terms with mass and stuff like that, based on what you're looking at. But anyhow, the thing I want to show you is, now you take a glass slab, and you have the refractive index varying like this. That is, at the center, it is equal to N0. Sorry, at the center, it is equal to R is 0, so it would be equal to N0 plus 1 at the center. And as you go away, this is like a Gaussian, so it's like a bell curve. So as you go away, the refractive index is changing. It is dependent on where you are. Right? How you can create this? You can just create a Gaussian pulse using a laser beam. And if that, or an electric field that looks like this. We will talk about what is refractive index, what is the molecular origin of refractive index, and then you will understand how we can, practically achieve this kind of a variation. But for now, we won't discuss that. But imagine that you can achieve such a variation, then refractive index is different in different parts. So based on how the ray enters, it would take a particular path, right? And that path is determined by this. And where is the information about the ray, which way ray enters? That would be encoded in beta. So if the ray enters from this way, beta would be one thing, another way, beta would be another thing, so on and so forth, right? And so for each thing you would get, based on where it is entering, and using the refractive index, you can sort of calculate very simply by solving this differential equation, what the ray would do. And here is the plot. It sort of orbits around the center. So no matter which way you go, it can never enter the center. Just orbits around. You have heard of black holes? This is a white hole. White hole is opposite of a black hole. It cannot enter that region. Right? And this is again similar to Einstein's gravitation and general relativity, because refractive index is like curvature. The reason I'm emphasizing on this is because I don't like the idea that you have to build billions of dollars of equipment to test something that is so natural to our world, that I should not have to have billions of dollars to build a large hadron collider or a LIGO or something like that to test whether a theory is valid or not. I should be able to sit under an apple tree and figure out. Right? So by comparing refractive index to curvature, what this opens up is it opens up so many possibilities to do all these experiments on a tabletop in my lab with an optical fiber and just an intense pulse of laser, which is very easily accessible. So in fact, let's look at a thing called gravitational lensing. It's a misnomer. Gravitational lensing is a misnomer in the sense gravitation is actually a really bad lens. But how does it actually change? What do you mean by gravitational lensing? So this is Earth, right? Let's say you're viewing some black hole here. What Einstein's theory says is, as we have discussed in the beginning, the planar around it is a physical substance. right? The space is not emptiness. It is not nothingness. It is something. It is a physical substance. It's not massive. It's a non-massive physical substance. So then the presence of the black hole or presence of Earth or presence of any massive object would then act upon the planar surrounding it, and that action is what we call as the gravitational field. Right? If it's a charge, the action would be electric field. If it's a current, that action would be magnetic field. If it's a mass, that action would be gravitational field. You may have heard that, from Einstein, that space bends. Right? So this is really a physical substance that's non-massive, and it bends. What do we mean by bending? It curves. And because it curves, light is going to travel along that curve. Well, however is the space, it's going to travel like that, just like how we have seen in the case of the refractive index. So whatever is the effect of gravitation from a black hole is the same as having varying refractive index. So then if you have a quasar or a star or whatever here, the rays of light coming from here, this need not be a quasar, it could be anything emitting light, a light source that's coming from here, then refractive index is different around the black hole or even the sun, right? Black hole is just much more pronounced, right? If you look at it in terms of magnitude. But then they should bend. And then from Earth, it would look like as if these rays of light, like a mirage, as if these things are coming from here. But actually the quasar is here. Right?
So would we be seeing two images of the same thing?
Yeah, sure. Cool. So now we can use Einstein's equations. There is something called the Schwarzschild radius. That means basically it's a, now you think about mass in general, right? So let's say electron. Electron is a physical thing. It should have some extension, some radius, right? You can determine it. It's roughly 10 to the power minus 15, minus 18 centimeters. But you can only pack so much mass into it, right? So there is a radius of the object itself, radius of the object, and then there is another thing called the gravitational radius. Or the Schwarzschild radius, which is given by something like 2gm by c squared. Where g is the gravitational constant, m is the mass, c is the speed of light. Now, if the object size itself is smaller than the gravitational radius, then you have a black hole. So from that, that's how you can come up with this. This 2gm by c squared is nothing but that radius. Below that radius, it's a black hole. So if you can pack all this mass into such a small size, then you get a black hole. And then we say space is curved, meaning the rays of light are bending, right? The rays of light are bending. That's what you mean as curvature. And so that's nothing but this. Right? Are you able to see how this is very closely related to? Okay. So now you can use this equation, and we have our other equation, right? D square x by dz square is equal to 1 over 2 beta d n square by dx. This is our equation, right? Here it is written in polar coordinates as r. Here I'm just writing it in Cartesian. It's just a matter of converting everything into the same coordinate system. But you see that I have a black hole here. The center one is the black hole, right? And the refractive index around the black hole is going to be changing using this. Now I can make my ray enter at different distances from the black hole. This is called the impact parameter. That is how close you are or how far you are. So something like this would be very far. This would be very close. Then, based on where it is coming from, it will bend. But you see, the closer it is, it's bending. Right? As you go farther, it's different. Now you see, if you hit a critical parameter, look at this purple curve here. Goes around the black hole. Now, if you hit the right thing, then what happens is, you see this black ring? The photons just accumulate there. They're just going around. Like you have seen the previous example, how they were going around. This has a name. Do you know what that name is? It's called event horizon. You heard event horizon? Interstellar, good movie to watch, right? So this is the event horizon. So you see photons, rays of light getting accumulated around event horizon. What does that mean? That means I can take a picture of black hole because photons are accumulating around it. Voila. Picture of black hole. So what is this ring? What is this ring of light? This is the black hole. What is this ring of light? That is the photons that are, accumulating, like how we just saw. Right? So essentially, when you are studying optics, you are actually studying the general relativity, really. And then optics, also we're going to look at wave optics, which brings you to quantum mechanics. So this is one of the nice ways in which we can integrate quantum mechanics and gravity, like quantum gravity. Do some cool experiments. Again, not $1 billion equipment, right? Maybe something that you can do in the lab. Because if man has to build billions of dollars of equipment to find out what nature is, that just doesn't sound right. I should be able to sit in my room and figure out, right? So in that sense, let me get back to this and show you one experiment that was already done in the last decade about white holes. So you create a refractive index variation like this, right? And then you see how the orbits are, right? The ray doesn't enter this region, right? So then now you can do this by taking an optical fiber. Take an optical fiber. In the center, you see the core. Around it, you see the cladding. And then you first shoot a pulse, very intense pulse. That's the yellow thing up there. So this is an intense pulse. So when you shoot intense pulses, what happens is this light is nothing but, we will see later, that it is electromagnetic waves. And these electromagnetic waves would basically change how the atoms in the material vibrate. And if it's a very intense light, then it's going to change these vibrations in such a way that the intensity of light changes the refractive index. So we consider refractive index as constant only for low intensity lights. If you have a high intensity light, then that high intensity light itself is changing the refractive index. So you can write refractive index in general as a function of intensity as some n0 plus some delta n, which is dependent on the I. These things are non-linear terms. So unless you have very high intensity, these won't become very common. So that's why you shoot a very intense pulse, right, which is, you can get a tri-sapphire laser, titanium, right, sapphire laser, and you can just get a femtosecond pulse that's very intense. And you shoot it through. So as this pulse has a shape. I can create a Gaussian shape distribution with this pulse. So as this pulse is moving around, going along, wherever this pulse is, the intensity of light is there. So the refractive index would change according to the intensity profile of that pulse. Right? So then I can create something like what we saw on the previous slide. Like I can create a refractive index profile like that. So then I, on the back end of this pulse, I send a very weak light. This arrow is very weak infrared light, infrared probe. So the pulse is moving ahead. Imagine this like a boat. Boat is going ahead, right? So it's creating waves in water. Then the next one is trying to go, but the motion of the next one is going to be affected by the waves left behind by the boat, right? So as the probe is going, it is seeing a refractive index variation due to the pulse traveling ahead of it, right? And so what happens is you have this kind of white hole event horizon where you have photons accumulating around a black hole, something like that. You have these probe pulses, getting accumulated. They're trying to move forward, but the refractive index is being changed by the pulse that's going before them. Right? Imagine someone is running ahead of you, and as they run, the medium, imagine it becomes more viscous. So if you're trying to catch up, they're running, you're trying to catch up, but it's becoming more viscous. So you are getting slowed down. Do you see that? So that's what you can sort of see by something called a power spectrum. That is, you pass all the wavelengths. The black curve is the wavelength of the probe without the pulse. There is no pulse, just the probe goes through, then you get the black curve. That's the frequency distribution. So you're sending in different frequencies or different wavelengths of light inside. Now the green line is the one with pulse. So there's a pulse going ahead and the probe is following it. Then because of the event horizon, right, the accumulation, you see a downshift. Some of the frequencies, some of the wavelengths reduced, but the frequencies have increased. They have the wavelength has gone down, shifted downwards. Are you following me? So experiments like this, which can be done on a tabletop or in a very simple fashion, can also reveal a lot about our understanding of general relativity. And optics and nonlinear optics is just one way to sort of achieve that. And so that's what I wanted to share in the lecture today, that you can do these kind of experiments in the lab. And the main take-home message here is that the refractive index bends light, and that refractive index is essentially like curvature. So you can draw a parallel with general relativity. And in fact, like for a black hole, you can sort of estimate a distribution of the refractive index, and then you see how light bends. And at a critical parameter, you get this, so you can picture a black hole. Right? Any questions? I hope you feel as excited as I do, but it's something really cool, because often when people try to think about these problems like general relativity, there is this thing that you need something very expensive, a huge effort to sort of look into this experimentally, right? You need telescope, this, that, or you can come up with some lab scale experiment, right? So, okay, that's it for today. Thank you.